right, we are going to talk about geologic time, and we're going to talk about fossils a little bit and how we know all this stuff. So the Earth was formed about 4.6 billion years ago, and that is an estimate, but it's a decent estimate. It's about when the solar system was formed. In order for the planets and everything to be where they are now, and how they are now, and the sun and how much fuel it's burned and everything, the solar system needs to be about 4.6 billion years ago. And the rock layers in the Earth show that it's about that long time. So the geologic time scale is a summary of the major events in Earth's history. There's not going to be things that are just little things like it rained a lot last week. And no, that's not going to show up in the geologic history. It's going to be big things. And it's divided into geologic time. So the eon is the largest segment of geologic time. And the epoch is the smallest segment of geologic time. And an area and a period are in between. So epoch is spelled E-P-O-C-H. It does not mean great and grand and wonderful, but we can totally make this epoch that we're living in a completely epic. I'm so sorry. All right, so there have only been 2 eons so far. If we look down here, we have the Precambrian eon and the Phanerozoic eon. The Precambrian eon ended with a large explosion that killed a lot of life. There were no dinosaurs on the Earth at this point, but there was still a large explosion that there's evidence of in the geologic history. And there was a lot of life that killed not all of it, and other life was allowed to develop. We live in the Phanerozoic eon, and if we look at the timing on these, right? So we live in the most recent one, obviously, because it's happening right now. So we're in the Phanerozoic eon, in the Cenozoic era, in the Quaternary period, in the Holocene epoch. So we're going to make the Holocene epoch pretty epic. So kind of a fun fact. So we look at these, and if we look at the Mesozoic era, that's where the dinosaurs were really on the Earth. And we always think, okay, the dinosaurs were all hanging out all together and everything was happy. And we always picture these guys all together. But like if you look at Tyrannosaurus Rex, it lived between 60 and 99 million years ago. So it was right around here. Kind of got into the tertiary period a little bit, but we're going to call it the Cretaceous period. So T-Rex lived in the late Cretaceous period. And then you have Stegosaurus, and we think, okay, Stegosaurus is going to be fighting T-Rex. No, Stegosaurus was down here in the late to middle and late Jurassic period, right? And it's kind of funny because Jurassic Park has a T-Rex as their symbol, and they were in the T-Rex was in the Cretaceous period. T-Rex wasn't even in the Jurassic period. Kind of a fun fact for you. So there are when we age things, there's 2 kinds of ages, right? There are relative ages. We know the order of events, but maybe not the dates. We know the Civil War happened before World War II, but not like exactly how far before World War II, right? We know the bedrock in Wisconsin formed before the glaciers came, but how much before the glaciers came, and how did that all work together? Or we can say, boom, we know the absolute dates. The Civil War was 1861 to 1865. World War II was 1939 to 1945. Boom, and we can be super accurate and super exact with those dates. Glaciers left Wisconsin about 11,000 years ago. Not as exact as Civil War and World War II because there wasn't anybody here writing this stuff down, but we can know pretty certainly, okay? So we use relative time to find the ages of rocks. And this is kind of a duh concept, but it's important to remember. It's called the law of superposition. So if you have sedimentary rocks that are not disturbed, the oldest rock layers are at the bottom and the youngest are at the top. So you think you put them down and you put another one on top, put another one on top, put another one on top. If nothing happens to those sediments, then they are undisturbed and the oldest is at the bottom. So if you look at this, A is the oldest, and then B gets put on top, and then C, and then finally I is put on the most recently. It is the youngest rock layer. So the law of included fragments, if there are fragments of one type of rock and they're found in another rock layer, the rock fragments must be older than the rock layer in which they are found. So let's talk about how this might happen. Let's say there's a huge flood and there's a bunch of rocks in this river, right? There's a flash flood and the rocks are being carried down the river and they're all dumped into a lake. So you've got a bunch of rocks at the bottom of the lake. So you've got the mud on the lake. The mud on the lake is not a rock yet. It's still mud. And then you've got all these rocks in it. And then the mud on the lake gets buried and it turns into a rock. But it's now a rock. It's like this muddy, soft, smooth rock with a bunch of big rocks in it. Those rocks that are in it are older because there were rocks before that. I was a rock when you were just a baby mud, right? So they were rocks before the other rock was a rock. Faulted and folded layers. Let's look at these. So if you have folding, so these layers were once straight, they got buried, the earth folded them, and now they're all folded up. The layers are older than the folding, okay? And if we look, like this top layer has been eroded away, so things aren't quite the way they used to be. Faulting is what happens when things move. The rock layers were put down, and then at some point, this D matched up with this D, and they were all on level. Things aren't going to be put down with a big jug in them. And then same with the C's and the B's. And if you look at this, A is completely gone over here. It's been eroded away. So the layers were put down before the fault happened. There's also things that happen that's called igneous intrusions, and this is a beautiful example of it. You've got a bunch of sedimentary rock, beautiful layers. And then there was some igneous activity and it almost got to the surface. Look at that, it almost got to the surface and didn't quite. So there's a bunch of lava, magma, because it never got to the surface, bunch of magma in there in an igneous intrusion. There's a little bit more in there, there's a little bit more in there. That igneous intrusion is younger than the sediments because they were there first and then it came along. And you can tell that because it kind of cut through them. And you can see like this white layer starts over here and it kind of finishes over here. These rocks have been folded a bit too. Nonconformity is a place in the rock where the layers of rock are missing because of uplift and erosion. So let's look at this. So what happened is we've got some layers, they got buried and they got all folded. And then they popped back up and erosion stripped away the top layers. And so now like this top layer that was there, it isn't there anymore. And that's an unconformity. Things just don't match up. Where's the top of this layer? Where's the rest of this layer? It's not there. And then another happens. So we've got an angular unconformity because this is all folded, this is all flat, and that's how that happened. So these folded parts are older than the flat parts. That's where that happens. See how this is all angular and then this is flat on top. This is all angular and this is flat on top. Okay, so we can match layers of rock to know their ages. So these guys are the same age and these guys are the same age. And there was something that happened in here that made it a little bit thicker, but these guys are the same age and these guys are the same age. So we can correlate them at outcrops, and outcrops are where the rock layers are exposed at the Earth's surface. A key bed is a thin, widespread layer, usually volcanic ash, that can be used to correlate an exact point of time. There was a volcanic explosion here and here, and we can say these were put down at the same time, and then we can correlate the rest. Radioactive dating, we can look back in time at the radioactive isotopes and see how old things are. Okay, let's look at how fossils form. All right, so let's look at some fossils. Fossils are remains of ancient plants and animals, and they're evidence that there was life there once. But fossils don't just happen all the time. Certain things need to happen first. And only a tiny percentage of living things will eventually become a fossil. I hope I become a fossil. That would be so cool. Odds are it won't though. So these are, there are ripple marks. These are fossilized ripple marks. These are, though, those are real ripple marks on a beach, that's sandy beach, and then they hardened into stone, and those are fossil ripple marks. So you can see how that happens if these ripple marks got buried right now, cemented together and became stone, they could become fossil ripple marks, okay? So there's mud cracks, right? Mud cracks. If it becomes fossilized, those are fossilized mud cracks. Okay, so when you're talking about plants and animals, it's usually the hard parts that are preserved. So bones, shells, the hard parts of insects like the exoskeleton, and the woody material of plants. like the wood, not the leaves as much. Now, it does happen with the leaves. So rarely preserved internal organs, skin, hair, and feathers. They just don't fossilize well. And if you do have fossils of skin, hair, and feathers, it's usually their imprints, not the skin, hair, and feathers themselves. You're not going to have a fossilized feather. You're going to have an imprint of a fossilized feather in a rock, just like we had like the imprint of the waves, you'd have an imprint of a feather. So types of fossils. So the original material, sometimes the original material is preserved. You get a bone or you get a piece of wood, and the minerals that it's buried in, it's buried in like mud, right? And so the minerals of that mud slowly replace the original material. Mud doesn't decay and turns to rock. Sometimes you get casts and molds. It's what happens like with leaves, and they make imprints in the rock. Some replacement, that's what happens with petrified wood. I talked about the original material up there. Carbonized films. So the carbon in the leaves becomes carbonized. And then trace fossils like footprints or tracks. So we know that there was the trace of that animal there. There's amber. So amber is what happens when you have tree sap that comes out of a pine tree and it hardens. And you can get insects trapped in that amber. And it's really, really cool. So the tree gets buried. This critter, this fly is trapped in it, and it's preserved forever. So there are some dinosaur tracks in Texas. So fossils occur almost completely in sedimentary rocks, and the reason is melting, a metamorphism, or igneous rocks. It would just destroy the fossil. The fossil would melt too. Sometimes if you have a low-grade metamorphic rock, though, where it just melts a little bit, it won't be hot enough to destroy the fossil. Or if you get trees that are buried by lava, those can be preserved as fossils. So in order to be preserved, organisms have to be buried rapidly after death and preserved from decay. And what happens is the burying helps preserve them from decay. If it dies and it sits out there, then it's just going to decay and it's not going to fossilize. If it's buried rapidly, then the minerals can replace that living tissue. So you have index fossils. So index fossils can help show the age of a rock. So index fossils are easily identifiable and they're short-lived. So trilobites are an example of a fossil. Trilobites were alive for absolutely forever. But they're only alive during one period. So if it's a trilobite fossil, we know it's during that period. So widespread occurrence. So trilobites were everywhere. So if you find a rock with trilobites in it, you know it's from that period. And they can be miles away from each other and still see there's this fossil, and we know that they're the same, that they happened at the same time. And that is everything. Let me know if you have any questions.